In 2014, BMW separated its high-performance two-door models from the traditional M3 sedan, establishing the M4 as its own dedicated coupe platform. The first generation, chassis code F82, was powered by the S55 engine, a 3.0-liter twin-turbocharged inline-six that produced up to 493 horsepower in its most extreme factory configuration. 7 years later, the second generation, G82 M4, debuted with the new S58 engine. It retains the exact same inline-six configuration and the identical 3.0-liter displacement class. This chart plots horsepower against engine displacement for the M4 lineage. Despite identical engine volume, the S58 pushes that ceiling to 543 horsepower and 479 pound-feet of torque, a 28% power increase and a 73 pound-foot jump over base equivalent models. An increase of over 50 horsepower from the same physical displacement is not the result of a simple ECU remap or turning up a boost controller. Overcoming the limits of a 3.0-liter block required a ground-up metallurgical redesign, replacing traditional casting with additive manufacturing and high-pressure electronic fuel management. To understand how BMW extracted this performance, we have to isolate the structural, induction, and thermodynamic variables altered between the S55 and S58 architectures. Pushing an inline-six past 500 horsepower generates immense cylinder pressures and rapid heat soak. The S55's open-deck block design faces strict physical limits in reliability when subjected to these forces. This cross-section shows the S58's primary structural solution, a shift to a closed-deck aluminum block. Notice the solid mass of aluminum surrounding the cylinder walls. This vastly increases structural rigidity, allowing the cylinders to withstand elevated boost pressures without warping. That rigid block introduces a thermal trade-off. A closed deck physically restricts the pathways for coolant to flow around the upper cylinders, creating a new thermal management bottleneck. To solve this, the S58 became the first BMW production engine to utilize 3D printed sand cores during the block casting process. Additive manufacturing allows engineers to print internal molds with highly complex geometries. These exact shapes are physically impossible to extract from a traditional metal casting mold. The resulting microchannels create intricate fluid paths that rapidly pull heat away from the combustion chambers, drastically improving heat dissipation under sustained track stress. To handle the increased rotational mass and load inside this reinforced block, BMW paired it with a forged lightweight crankshaft and forged connecting rods. This combination of closed-deck rigidity and 3D printed thermal management allows the S58 to survive cylinder pressures that would cause catastrophic failure in earlier engine architectures. Both engines utilize twin mono-scroll turbochargers. Assigning one turbo to service exactly 3 cylinders minimizes the volume of exhaust gas required to spool the compressor, reducing turbo lag. The S55 managed its standard 17.4 psi of boost using pneumatic wastegate actuation. Pneumatic systems rely on vacuum-driven mechanical linkages. This creates inherent lag, meaning the hardware cannot react instantaneously to fluctuating commands. This schematic compares the two induction systems. The S58 upgrades to slightly larger compressor wheels paired with fully electronic wastegate control. Electronic actuation replaces vacuum lines with a direct solenoid, enabling millimeter-precise, instantaneous adjustments to the wastegate valve position. Mechanically, this means the S58 can quickly spool to and safely sustain a much higher peak boost pressure of 21.7 psi in competition models. This electronic precision prevents dangerous boost spikes that cause detonation, keeping the turbochargers strictly within their peak thermodynamic efficiency map. This induction architecture is reliable enough to serve as the exact hardware foundation for BMW's modern GT3 endurance racing programs. Electronic wastegates provide the necessary computational precision to manage a 21.7 psi air charge without destroying the engine block. Forcing 21.7 psi of dense air into a cylinder requires a perfectly matched fuel mixture. Failing to deliver enough fuel causes the engine to run lean, leading to immediate thermal failure. The S55 utilized high-precision piezo injectors operating at 200 bar of pressure. The S58 upgrades to a high-pressure direct injection system, generating a massive 350 bar. This diagram shows the physical chemistry behind the change. Increasing injection pressure from 200 to 350 bar results in a significantly finer fuel mist. These finer droplets have a much greater surface area to volume ratio, creating a faster, more complete combustion event. Complete combustion lowers total emissions and provides crucial detonation control under extreme cylinder temperatures. This fuel delivery works in tandem with double Vanos variable camshaft timing and Valvetronic valve lift, which carry over from the previous generation to eliminate traditional throttle body bottlenecks. At 350 bar, ultra-fine atomization acts as a thermodynamic tool, stabilizing the violent combustion cycles required to consistently generate over 500 horsepower. We can track how this metallurgical and computational evolution translates into empirical performance data on the tarmac. In acceleration metrics, the second-generation M4 Competition X-Drive drops the 0 to 60 time to 3.4 seconds, with the CS model hitting a staggering 3.2 seconds. Sustained track capability over the 12.9-mile Nürburgring Nordschleife provides a clearer picture of total thermal endurance. The absolute pinnacle of the S55 generation, the track-only M4 GTS, managed a 7:28 lap time. The S58-powered M4 CSL shattered that benchmark with a 7:20 lap time, an 8-second improvement in motorsport metrics. Because of the factory thermal management and forged internals, the S58 arrives significantly over-engineered for its stock power output. This chart outlines aftermarket tuning potential. While the S55 safely reached 600 horsepower, the S58 pushes the tuning ceiling past 700 horsepower. Achieving these figures in the S58 requires only ECU software tunes and standard bolt-on modifications, without ever opening the engine block. The Nürburgring times and aftermarket tuning data prove the S58's hardware is designed to operate well below its true structural limit from the factory. The jump from the S55 to the S58 illustrates how engineers break the thermal and structural limits of a fixed engine displacement. Additive manufacturing enabled the cooling geometry, a closed deck provided the armor, and electronic actuation delivered the precision. Despite industry shifts toward electrification, this engineering sequence proves the internal combustion inline-six has not yet reached its developmental plateau. By optimizing the M4's power plant at the level of fluid dynamics and metallurgy, BMW M established a new performance limit for the compact executive sports car.